My title is, in fact, Chief Internet Evangelist. It wasn't one that I asked for. I asked for Archduke, and they said that it didn't fit in the HR thing. Why don't you be our Chief Internet Evangelist? So that's the job I have. So let me start out by warning you that we should be careful in our day's deliberations because machine learning and artificial intelligence tends to be rather narrow. It's very deep, but it tends to be rather narrow. So don't overstate or overestimate what these systems are capable of doing. However, I've been told that you start all these things with jokes, and I can tell you that our home assistant is capable of telling jokes. You say, "Tell me a joke," and it'll tell you a joke. So I asked it to tell me a joke, and it said, "What do you do if you're afraid of elevators?" And the answer was, "Take steps to avoid them." -2. I don't know, I think we hired some joke writers. Well, I have another warning for you, and that is, first of all, I'm a computer scientist, I admit to that. But second, I'm not an AI expert. So I don't know what I'm talking about. But that never stopped me before, so here we are. So, what is this AI stuff? Well, some of it sort of falls into analytic programming, the ability to gather large amounts of data, analyze it, and come to some conclusions. That's true of many things that aren't called AI, but a good portion of artificial intelligence and the manifestation of it is a consequence of doing this kind of analytic programming, where you know what you're doing, you know the area of discourse, and you have models that, from which you are trying to derive conclusions based on data that you've collected. There are, in the game playing, of course, there's what moves can you make, and can you build a tree of all the possible moves that you could make. And for some simple games, you can actually draw the entire tree of moves that are possible, like for tic-tac-toe and things like that. On the other hand, there are decision trees, which are often used in business development. They're often used in military campaigns. They're used in a series of, like in crisis situations where you're trying to do triage. You have a set of conditions, and you ask if these conditions are fulfilled, then what should I do, or what's the probability that X, Y, or Z will happen. So these are also helpful tools that sometimes manifest in artificial intelligence programs. Alpha-beta pruning is a concept where you look at all the possible cases, or as many as you can, and if you reach a conclusion that going down a particular path is not useful, then you just clip that path off and you never consider it again, even if, for example, a board game gets into a configuration where you would have gone down that path again. If you've already analyzed that, you don't do it a second time. It's an efficiency step. And in the early stages of exploration of artificial intelligence and game playing, this was necessary because the amount of memory available in the computers was so limited that you had to find ways of constraining the amount of data that you had to hold on to in order to exercise the algorithm. Expert systems that Ed Feigenbaum and Josh Lederberg pioneered at Stanford, the one that immediately came to mind was heuristic dendral, which took information about mass spectrographic data and tried to speculate about what kinds of molecules would have produced that particular mass spectrogram. And it was actually quite a successful program. It was rule-based in the sense that you said, if this, then that. And you'll find many, many cases where these sort of rule-based systems show up, not only in this case of trying to identify particular candidate molecules that would produce a particular spectrogram, but also in the analysis of crisis situations, triage, and the like. You create a whole series of conditional expressions, and you follow those as data becomes available. Bayesian analysis, which I'm sure many of you are familiar with, is a very refined statistical method which looks into conditional probabilities and tries to help estimate what the likelihood is of something happening, given that something else has happened or given that some other piece of data has become available. This is important because often you don't have all the data that you would like in order to come to a conclusion or make a choice. And so the Bayesian analysis allows you to exercise choice even in the presence of limited or partial information. It's become a very powerful tool. And the Reverend Bayes, I'm sure, would be unhappy about this because when he developed his formula, he thought it was useless and he was proud of that. And of course, it turns out that it's so fundamental to everything we do at Google that we might as well call ourselves Bayesian analysis as opposed to Google, but Google is a more interesting term. It's a misspelling, by the way. The two founders intended it to be Googol for 10 to the 100th. The lawyers, unfortunately, had never heard of that, so they wrote Google because that's what they thought they heard. They actually registered the company with that name, and by the time the founders found out, it was too late. So we're not the name of the company that we thought we were. So there's a layman's definition, though, of all this, and my favorite one: if it doesn't work, it's AI. or if it doesn't work all the time, it's AI. If it does work, it's engineering. The consequence of this is that as we got better and better at AI, it stopped being AI and became engineering. And so we've now reached the point where engineering is, of course, a very powerful tool here. One thing which has become very important on the scene recently, it was explored many, many years ago in the form of things called perceptrons, or things that emulated the kinds of models that we have of the way our neural systems work in our brains. What's happened, though, in the recent past is the ability to build extremely large-scale, complex and multi-layered neural networks. And our ability to operate at scale has transformed the kinds of things that these neural networks can do. The basic concept is fairly simple. There are inputs that go in at the bottom here into two nodes. There are weights associated with outputs coming from those nodes, and they're combined in some fashion to produce an output. And you can imagine that this is a very trivial case where we're basically taking the inputs and then multiplying them by the weights and then combining them in some fashion to produce the output at the top. Imagine, though, large numbers of nodes, large amounts of weights trying to produce an outcome that you're looking for. And the training mechanism, the feedback loop here, which is called, I think I have a slide on this called, let me go over here. So the inputs get applied. We calculate the actual versus the desired output. So the Y thing sticking out the top there is the actual output. Y prime is what you wanted. The difference between the two is error. And so the whole point here is to propagate backwards the error into the network and change the weights in order to minimize what the error would be. And that's the learning cycle that goes on. So you train these networks repeatedly by offering them inputs, observing what they produce as output, and then adjust the weights in order to get closer to the answer you were looking for. And that's a very rough way of describing what's going on, and you just repeat this process over and over. Now, something I want to emphasize about this is that the system ends up having, especially a very large-scale system, has many, many, many of these weights associated with the various nodes in the net, or the linkages in that network. It turns out that if you opened up a box full of this stuff and you looked at it, you'd see 1 million dials with various values. If somebody said, what happens if you change the dial by this much? No one knows what the result will be. This is a trained system, but we can't predict exactly what happens when you change anything. We know that we can keep sending in samples, examples, and feeding back our reaction to what the system says, but we don't really have a deep understanding, at least I don't, of predicting what will happen with these networks. And so when you discover that it doesn't do what you wanted it to do, you have to train it with new samples in order to get it to change the weights to get an output that you want. And so this is not the same thing as opening up the code and just going in and analyzing it and changing a couple of expressions somewhere. It's a much more, in some sense, cumbersome process. And I think I want you to, at least I want to convey to you my impression that this is still a kind of iffy process, and it's not one that we have a deep understanding of, despite the fact that we can make it work. It's kind of like electrons. We don't know what they are, but we use them all the time. And so here we are with the moral equivalent of that. So language translation is another example of an area that's made substantial progress over time. Way back in the 60s when I was at Stanford, we thought we could do this easily by just sticking an English and Russian dictionary into the system. But we gave it out of sight, out of mind, and it came back with invisible idiot. So we decided maybe there was something missing in translation. more recently, we discovered that we could use statistical analysis to say that if we had lots and lots, a corpus of lots of documents that purported to be the same document in different languages, then you could identify phrases in each of the two documents that had a high probability of being the same phrase in the two different languages. So actually, statistical analysis worked quite well. And for quite a long time, that was the primary means by which language translation was done. In fact, it was so good that that was the major advance over many years. But more recently, we sort of pushed the limits of statistics. And of course, you rely very heavily on having a large corpus of documents in two languages or more. So more recently, at least at Google, we've been again injecting sentence structure, grammar, and things of that sort, and semantics, in order to improve the quality of the translations. And most recently, we've actually introduced some neural networks into the picture as well, and with a noticeable improvement in our ability to recognize common phrases and to translate them. In fact, we even have situations where you might have a phrase in English and you have a similar translated phrase in French, but you didn't have one in German, but you go through the French to get to the German. So there are these kinds of linkages that are starting to show up as well. It isn't perfect, though, and so here's what happened to me in Lindau, Germany, at the Nobel Prize meetings last May. I had looked up the weather in German, and it automatically translated that page into English. But you noticed that it said that there was a 0 probability of ice cream. And so I was asking, hey, do you guys have, does it snow ice cream here? And he said, no, actually the word in German was EIS, ice. And so that turns out to also mean ice cream. And there wasn't enough context for the translation system to realize that this was not ice cream, it was just, hail. So we got the wrong translation, and everybody enjoyed that. One thing I can tell you is that a lot of the advances in artificial intelligence have manifested in the form of game playing. And so some of the most interesting results are illustrated by that. This is an attempt to program things to achieve human-level execution of a game. Again, I want to emphasize that we should not imbue these programs with human-level cognitive, generative problem solving just because they can play a game. And it's a tempting thing for people to do. It says, well, if it can play the game better than I am, maybe it can do everything better than I can. And that is not a very good conclusion. Checkers was one of the first fairly complex programs to be tackled by Arthur Samuel, who coined the term machine learning way back in 1959. And he invented or made use of the notion of search trees and alpha-beta pruning, and also representations of board positions so that he could tell if he'd been in that position before he didn't have to analyze it again. And again, he was trying to save space on the computers that he was programming at the time. Chess, of course, has had the dramatic example in 1997 when Deep Blue beat Garry Kasparov for the first time. Kasparov had won in the 6-game series in the preceding year in 1996. He won 4-2. But in 1997, Deep Blue won 3.5 to 2.5. And what was very interesting about this game is the psychology of it. In the first game, in Move 44, the IBM Deep Blue did something that Kasparov couldn't understand. And it bothered him a lot, and he went off and thought about it for a while, thinking that the machine had done something that was deeply intelligent that he didn't understand. It really spooked him. He won the game anyway, and then went on to lose the next game because I think he'd been spooked. It turned out later it was a bug in the program. It just was a random move that it wasn't intended at all. And so this is a good example of imbuing the machine intelligence with a little more depth than it really has. But it certainly put Kasparov in trouble. Now, the most recent and exciting result was from playing Go. And the AlphaGo program from DeepMind that now is part of our Google, an Alphabet company, starts out. They played Lee Sedol, who is a 9-dan expert that's the highest you can go, playing Go. AlphaGo won 4 games out of 5. And in the first game, Move number 37 caused quite a bit of trouble. Lee went off and wandered around for 10 minutes trying to figure out what the machine was trying to do, because it was not an intuitive move. It was not one that an expert player would have made, and yet the machine went on to win. And so people have imbued the program with this depth of understanding of Go on the basis of observations like this. One of the most important elements that led to the AlphaGo's success is that it was a 150-layer neural network. And this is compared to, 1 or 2 layers of neurons that had been used in the past. And so managing to scale up to that complexity, I think, contributed very greatly to what the AlphaGo system was capable of doing. We developed at DeepMind a physical device called the Tensor Processing Unit. Now, you're all familiar with CPU, Central Processing Unit, and some of you will have heard graphical processing unit, or GPU, which is often used to generate images in interactive games. It's a very, very rapid kind of processing for image production. TPU is a new entry into machine architecture, and it indeed is a complex and multi-layered neural network. So we have several different kinds of computing going on, not counting quantum computing, which we're not talking about today. What this means in the computer science world, from my point of view, is a richness of exploratory landscape, of possibilities of computation that we didn't have before, and that's very exciting for all of us. Here's an interesting application. We used the Tensor Processing Unit to play the Go game, but we also thought maybe we could apply this to a practical problem. As you know, we have data centers around the world, and they are very large-scale systems. They consume a lot of power. I mean, we're talking somewhere in the neighborhood of 128 to 256 megawatts of power required to drive these systems, and you can imagine that it generates a lot of heat. And so we have to work hard to cool these systems off. And the traditional way of doing this was to gather quite a bit of data about how well the pumping system had worked, which consumes a lot of electricity on its own. At each week, we would adjust a lot of the parameters manually in order to try to do a better job of controlling the cost of power, the amount of power required to do the cooling. So we decided to train a Tensor Processing Unit to do this. And at the end of a week or so, as I recall, the system was able to reduce the power requirements by 40%. Now, that was really significant. So immediately we went off to do the same thing at the other data centers. But a 40% reduction is astonishing from my point of view. 4% would have been, sort of, oh, well, that's pretty good. But this was quite surprising. So it tells you that the depth of capacity of these sorts of systems is extreme for narrow kinds of applications for which it's easy to state the optimal function, the optimization function, or the function you're trying to optimize. In this case, we're trying to reduce total power requirement. When you don't have a simple way of expressing success, it gets harder. I mean, it's one thing to say, yes, it's a cat, or no, it's not, or it's a dog, or no, it's not. But if it's a more complex question that you're trying to get the system to respond to, it's a lot harder to do that. So I thought I would finish my part of the talk with a little video of a much more complex system that Google has been exploring since, actually for about 5 or 6 years now, and that's getting cars to drive themselves. And I think for just a moment about the kinds of things that you would have to do, the kinds of software you'd have to write in order to successfully navigate in traffic in San Francisco. So this should give you an idea of what that's like. This is our first model car. We have several new ones now, as you may know.
Look, Ron, no hands. No hands anywhere. No hands. No hands. I love it. So we're here at the stop sign. Yep. Cars using radars and laser to check and make sure there's nothing coming the other way. I find myself old habits die hard, man. They don't die. Hey, anybody up for a taco? Yeah. What do you want to do today, Steve? I'm all for taco though myself. All right. Well, go get a taco at the drive-thru. And we're turning into the parking lot. How? There we go. Now we kind of creep along here. Does anybody have any money? I've got money. No, I've got my wallet right here. You can roll down your window and order a burrito. Yeah, put that. I'm doing very well. How are you today? This is some of the best driving I've ever done.
95% of my vision is gone. I'm well past legally blind. You lose your timing in life, everything takes you much longer. There are some places that you cannot go, there are some things that you really cannot do. Where this would change my life is to give me the independence and the flexibility to go the places I both want to go and need to go when I need to do those things.
You guys get out. I've got places I have to go. Bye now. Hey, it's been nice. It's been nice.
So I'll finish there and invite questions, and thank you very much for your patience. We do have someone else from Google who is more an expert than I am on this topic, so I hope I haven't embarrassed the company with my simple-minded discussions. But thank you all very much for listening.